Hello everyone. In this video, we'll be dealing with the instruction set. Before understanding how the control unit interprets a particular instruction and accordingly sends out control signals, we first need to understand what an instruction looks like. Okay, so we are aware that on the back end, all that computer understands is a series of zeros and ones. How is that series of zeros and ones interpreted by the computer is what is defined by the instruction set. In this particular lecture, we'll study about the instruction set of JC62 machine. So it is predefined that the instruction of a JC62 machine, any instruction that JC62 machine can understand, interpret and perform has to be 12 bits long. Okay, so also one clarification. I do not write this series of zeros and ones. What I write is a program that is human understandable. For example, in case of JC62, I will write add C3. Alright, on the back end, the compiler will convert that instruction add C3 into a 12-bit long instruction of zeros and ones. I'll not be writing a sequence of zeros and ones. It is the compiler that converts my human understandable add C3 code into a series of zeros and ones. Fine. So now I have that series, 12-bit series. Of those 12 bits, the first 4 bits represent my opcode or the operation code. What operation code does is it tells the control unit what operation needs to be performed, whether I have to add, subtract, load, jump, move, what exactly I have to do is represented by my operation code that I mentioned in my instruction, and on what particular thing I have to perform that operation, that is told to us by the operand. Now, if you remember from the last lecture, I mentioned that any data that JC62 is compatible with has to be 12 bits long. I also said in this lecture that the instruction is 12 bits long, out of which 4 bits are already reserved for the opcode. So definitely I cannot store the data on which this operation is to be performed in my instruction. But out of these 12 bits, since 4 bits are already utilized, I do have 8 bits remaining. And what is 8 bits long? The address of data that is stored which is compatible with the JC62 machine. So the data is 12 bits long, but the address at which that data is stored is 8 bits long. So in an instruction, I do not store the exact data, rather I store the memory address of that particular data in my instruction. Okay, so the instruction is 12 bits long. The first 4 bits represent what operation needs to be performed, and the next 8 bits tell me on what particular data I need to perform that operation, where that data is stored in my memory. That address is given by the next 8 bits. Here it's written that instructions that have 2 operands, the other operand is always contained within the accumulator. See, whenever I have to add two numbers, I need two numbers. I cannot say add 3. Add 3 to what? So if I write add along with a memory address, so add that number to what? JC62 inherently understands it as add whatever is stored at this particular memory location at that number to the number that is stored in my accumulator. So if it is a single operand instruction, suppose if it is a load instruction, so I'll simply say load. Load is represented by a 4-bit long opcode, and then I'll give a 8-bit memory address. We'll see this load example in the upcoming slides. If you don't get this part, it's all right. But if you want to understand, the load part is given by these 4 bits, and the next 8-bit represent on what location I need to load that particular data. From what location I need to fetch that. Okay, so in load instructions case, just one operand is perfectly fine. But I say add C3. So I need to add whatever is stored at C3 location to something, and that something is stored in my accumulator. Fine. Now coming to this table. This table summarizes the entire JC62 machine. If you are able to understand and interpret this particular table, you are thorough with JC62. In this video, we'll be focusing on these two columns of this table, and the subsequent videos will cover all the other columns as well. So these are my instructions and these are their corresponding opcodes. See, here we have written that the opcode is 4 bits long. If you know a little bit of binary, we know that with 4 bits I can represent total 16 numbers with combinations of zeros and 1. It can be the 0000, 0001, 0010 up to 1111. So I can in all represent total 16 numbers with the help of 4 bits. Fine. However, in JC62 we have utilized only 8 of those bits. We only have 8 instructions. What I want to say is, using 4-bit long opcodes, I can define 16 unique instructions where 2 represents some other instruction, 3 represents some other instruction, 4 represents some other instruction, 15 represents some other instruction. But in JC62, we have only utilized 8 out of those 16 combinations possible. So I have my load instruction, which means that I will take data from a memory location and store it in my accumulator. Store instruction does the exact opposite. It takes data that is stored in the accumulator and stores that particular data into a memory location in our memory. Add, as I said, adds a number to another number that is stored in the accumulator. Subtraction subtracts. Move moves my data from accumulator to the B register. Jump and jump negative are branch instructions. We'll study them in detail later. Halt is used to stop my particular clock. So corresponding to these instructions, we also have opcode. What does opcode tell me? Opcode basically helps the control unit map my human understandable instruction to something that the computer will understand. So whenever I write LDA, compiler will convert that LDA into its corresponding opcode. LDA's opcode is 1. So compiler will convert my LDA into 4-bit long binary 1, so that my control unit knows that since I have 1, I have to perform LDA operation. Things will get more clear with the help of this example. I already told you that load instruction transfers data from a memory location to the accumulator. Opcode of LDA is 1. Fine. How will I write this instruction? Well, suppose I have to load whatever is stored at C3 location in my memory into the accumulator. I will write LDA C3. And on the back end, the compiler will convert this instruction into a 12-bit long series of instruction. How? LDA, as we saw, has an opcode of 1. So this LDA gets converted into 0001. We can see 4 bits were reserved for my opcode, hence 4-bit long 1 we have written. And the binary equivalent of C3 is 11000011. So this C3 also gets converted into its binary equivalent. Now I have this 12-bit long instruction. The first 4 bit of which represent my opcode. This opcode is 0001, corresponds to the load instruction. So my control unit now knows that I have to load something. Load something from which location? Location is given by the operand that is 8 bits long. So this LDA is converted into this instruction, which my control unit now understands and will send corresponding control signals to the data path section for this instruction to be performed. I really hope that now you know what these 12 bits are. The first 4 bits represent my opcode. The next 8 bit represent the location of the data on which I want to perform this operation, and how do we exactly map these operations to their opcode. It is given in this particular table. All right, thank you.